Okay, with Green's Theorem homework due tonight, does anyone have any questions on it?
Ooh, I do. I don't remember the name.
Well, I'm going to go on a limb and bet that. So I have a question number 4, because that's one of the ones that doesn't have an example.
Mm-hmm. I think that's it.
Okay. All right.
Oh, that's it.
Okay. Yeah, I've gotten questions about that one already. Okay. So. So it's asking, evaluate this line integral where, okay, based on the numbers I have, f is vector field of these components, 3x y squared, 4x cubed plus y. And for convenience, I'm going to label these as I normally would, p and q. And the curve C, well, are most easily drawn. So it is a semicircle. So we have this boundary, so this part of the x-axis is included. So the line segment from -1 to 1, and then traveling one circle in this direction. And they tell you, assume the curve is oriented counterclockwise, which is what you want for applying Green's theorem. The curve it's not really a semicircle. Thinking of a different problem. Alright, x goes from 0 to pi, y equals sine x, so it's still a hump, but it's not a circular shaped hump. But still with this orientation. Okay. So it's described by the inequalities. X goes from 0 to pi, and the y goes from 0 to sine x. Okay. Now, if you approach this problem by thinking, okay, what are parametric equations for this part and parametric equations for this part, and evaluate this directly, that's not what you're supposed to do. In a way, you're actually making it more difficult for yourselves. So the point of this problem, really this whole section, is to work out these kind of line integrals by applying Green's theorem. So this line integral can be written as p dx plus q dy for these p and q right here. But then when you apply Green's theorem, so C is the boundary that includes both pieces, and D is the interior. So Green's theorem says that this integral that you want is equal to the double integral over the interior of qx minus py. Okay. So you're actually evaluating a double integral, and the convenient thing about this problem is the setup is given. So you would have, so x is the only one that has constant limits. And then you have 0 to sine x as your inner limits. And then you just need the appropriate partial derivatives. And that can help simplify things. For instance, qx, we're going to forget about this y term. So in this, with these numbers, you'd have 12x squared minus dp dy, which is what?
6x.
Yeah.
6x1.
Assuming I heard you correctly from my own sneeze. That should be, 6xy. Okay, so there's no need for parametric equations or anything like that. You can just go ahead and start evaluating this. First integrating with respect to y, and so forth. Okay, before I say anything else, are there any questions about the setup of the application of Green's theorem?
Just to be clear, like the R vector there, it's just the derivative of f, correct?
This?
Yes.
Oh, okay. What this refers to is the fact that if you were to evaluate this directly, you would have some integral from a to b, where those would be your parameter values from a curve of f with your parametric equations plugged in, dot product with r prime of t dt, which you can think of as dr. So that's the reason for this notation to describe the line integral.
Okay.
Yeah. And while the line integral in most cases, the line integral can certainly be done that way, the idea is Green's theorem gives you another way to do it.
So did you already write what R is, or is it just?
The nice thing is, in this problem, you never have to. Because if I were to describe this boundary, I would have to do it in two pieces. That's one of the reasons why we'd rather use Green's theorem, because at least now there's only one integral to do. So C I could describe as a union of two curves. I can call this line segment C1 and this hump C2. So C1 would be x is equal to t and y is equal to 0. T goes from 0 to pi. And then C2, you can again say x is equal to t, and now it's tempting to say, well, actually, I'm not going to do that. I'm going to say x is equal to pi minus t, y is equal to sine x, but that again would be pi minus t, and t again goes from 0 to pi. Now, can anyone tell me why I could have done x equals t and y is equal to sine t, but why would that not be correct for this problem? If I just let t run, if I say t and x are the same thing, and let t run from 0 to pi, that was perfectly fine for the line segment, but why is it incorrect to do that for this piece?
It travels the other direction.
Yeah, it goes the wrong way. It's an incorrect orientation. So as long as your t has a minus sign, and it to indicate that you're going to go from right to left, then you can come up with parametric equations that work. And this is a logical choice because then I could have t going from 0 to pi, and I could write this as a sum of two integrals, one over this piece, one over this piece. This one wouldn't be too bad because at least your dy dt would be 0. That would cause one term to drop out. So if you were to do it directly without using Green's theorem, that's what would be involved. And it is. Hopefully Green's theorem gives you something nicer. Although, if you were to go ahead and do it this way, and you go ahead and integrate with respect to y, things get a little rough after that. Because you, for instance, because you integrate this with respect to y, and what are you going to get? Just that piece.
6x. Integrate.
Integrate.
Okay.
3xy squared.
Yeah, 3xy squared, because you get 6x as a constant, then you get y squared over 2. That simplifies to
3xy squared.
3xy squared. And then you plug in the limits for y, and that leaves you with 3x squared as 3x sine squared x. Now, dealing with sine squared x, if it's the only trig function present, is no fun. Try trig identity. Sine squared x is the same as 1 minus cosine 2x all over 2. But then you're left integrating something of a form x cosine 2x. And over here, you integrate this with respect to y, you get 12x squared y. And you can plug in, so you have like 12x squared sine x. How do you handle functions like that?
Would you just pull out the sine squared?
No. So if you have something like, x squared sine x or x cosine 2x, what integration technique do you need to use? What? No. There are only so many you learn in Cal 2, so go through the list.
Integration by parts.
Integration by parts. So anytime you have some power of x, and then like sine or cosine, doesn't matter, of constant times x, something like this, use integration by parts, and you need to perform it n times, because every time you do integration by parts, keep whittling down the power of x until it's all gone. And you let your u be the power of x, and then your dv is sine x dx, because at least sine can be easily integrated. So you keep flipping back and forth between sine and cosine and lower powers of x until there's nothing left. But again, if you were to stick with this form and do it this way, you'd also have similar combinations of like powers of t and trig functions of t. So there's no free lunch here. So you're probably better off to sticking with this approach. But so this definitely tests your Cal 2 skills. Okay. So any questions about how to proceed with this one? Okay. Yeah, this one looks a little too time-consuming to put on a test, but but I'm here to test your Cal 4, not your Cal 2, as much. Any other homework questions?
Number 8.
8.
I kept working it out, and I kept getting an answer, but every time my answer was wrong.
Okay. Okay, so here you're trying to find area. Okay. All right, so Green's theorem for area is that this is your region D that you want the area of, and it has this boundary that's a closed curve C, then the area of D, which is the double integral over D of just 1, can be described as 1/2 the line integral over the curve C of x dy minus y dx. So x is playing a role of your q, of your vector field, and then minus y is playing a role of your p. Because then you take, so you take qx, dq dx is equal 1, minus py, so that gives you your integrate of 2 over 2. So this is just using Green's theorem backwards. So the parameterization of this region bounded by these parabolas. Lost you. So the first one is t and t squared as your parametric equations, and then the other x is t and y is 12 minus t squared. Now, it's kind of unusual to see parabolas described using parametric equations, but since x and t are the same thing, this is the same as y is equal to x squared, and it's the same as y is equal to 12 minus x squared. Okay, so here's y equals x squared. And then 12 minus x squared would be over here. So it's this region that you're trying to get the area of. This is your region D. So I can describe the curves, the boundary curve C of this region as union C1 and C2. So C1, in counterclockwise orientation, so C1 is going in this direction, and then C2 is going in this direction. Now, certainly this line integral you can break up as line integrals over both pieces and just add them together. So if I were to break this up, all right, so C1 plus integral over C2. Okay. Now I don't know if this will cause you to get the wrong answer, but a common mistake with these kind of problems is to not take into account the orientation. Here, the C1, the straightforward orientation is from left to right, but then you have to reverse it for this one. And what you might be better off doing to handle the orientation most easily is, since C2 is oriented this way, work with minus C2. So I have minus integral over minus C2. And what that allows you to do is go ahead and use these parametric equations as is. So what you can do is, so for example, for this one, you can write it as the integral from a to b. These are t values, and x is t. Dy, okay, is 2t dt minus y, which is t squared, and then x and t are the same thing, so dx equals dt. So you can handle it that way, so you get a reasonable integral to do. And then similar thing over here with these parametric equations. Now, what's missing? Well, what do we still need to know before these can actually be evaluated and get a number? Yeah, the limits A and B. I haven't written those down yet. How do we get the limits? What? Yeah, that's where we intersect. So you set these, so your y values intersect. So you set these equal to each other. So to get the limits, you solve the equation x squared is equal to 12 minus x squared for x. And you're going to get two values. This is a quadratic equation. They'll be plus and minus of each other. And that's what you fill in here for your A and B, because x and t are the same thing in this problem. Yeah. So as long as you pay attention to the orientation, then you can use whichever parametric equations are most convenient. Just make sure that everything's kept counterclockwise, and if your most straightforward parametric equations don't give you something that's oriented counterclockwise, that's okay. Just change the sign, like was done here. Questions on this one? Or any other one?
Where'd your y come from? The t squared dt.
Oh, from here. So I'm just filling in x dy minus y dx, and I'm using these parametric equations. Yeah, because these are your x and y components.
And then you use the second r for C2?
Yeah. Yeah, so here x would be t again, and y would be
12 minus t squared.
12 minus t squared. And then you'd adjust your dx and dy. Well, dx would still be dt. But here dy would now be minus 2t dt. Any other questions? Okay. You ever questions on this homework? Okay. Now, so we only have 2 sections left. And I budgeted today and Friday for the second last one, and I don't really need that much, so I'll probably do some homework questions today. It'd be a good idea as we get into the last week to whatever homework is coming up due to have some questions ready, because chances are we will continue to have some time in class for homework questions. Okay. And you should start looking over the final, because right now we've covered enough that you could do most of a practice final. There's really just the last couple problems on Stokes Theorem and Divergence Theorem that we haven't got to yet. Stokes Theorem we're going to see now, so that we can spend some time next week. And the last day of class, that'll be all review, but if we could do some review before then, of course, I'm sure you guys would prefer that. Okay. Okay, so the next theorem that we have to re-express certain integrals by using derivatives is really a generalization of Green's theorem to 3 dimensions. So Green's theorem for a plane region says that, as we just saw in the homework problems, that the line integral of a vector field on a closed curve C is the integral over the interior D of qx minus py, where f is equal to pq, where it is required that your closed curve C have counterclockwise orientation. But another way to describe Green's theorem, and I pointed this out a few lectures ago, is qx minus py can also be written as the curl of f dot product with a vector k, which is pointing up in the positive z direction, because that is if you have a plane region, the same thing viewed in 3 dimensions, vector k is your normal vector, because now if we view this region D not just as a region in the plane, but also as a surface S in 3 dimensions, like the kind of surfaces I've been talking about lately. It's just that because it's a plane region, this surface is completely flat. So its normal vector is always pointing in the same direction, pointing in the direction of k. So we can view Green's theorem this way. And this is not really needed for Green's theorem problems, but it paves the way for Stokes theorem. Okay. And keep in mind, this is someone named Stokes, not someone named Stoke, and we have apostrophe S. So if we don't get that wrong, it's not enough. Now, this says that so this is a 2D theorem, Green's theorem. Stokes' theorem is truly 3D. That again, you have some closed curve, but now it's in 3-dimensional space. And now we have this closed curve. And I've used this analogy before. Think of it like a Lay's potato chips. You have some warped membrane, if you will, and C marks the boundary, and S is a surface that is the interior, and the line integral of your vector field F around this 3-dimensional curve C is the integral over the surface S, and you take the curl of F, dot product with the normal vector, and you integrate that over the surface. The only difference is, here the normal is always pointing in the same direction. Now the normal can vary as you move around the surface. So it's actually a function of x, y, and z. But we see that Green's theorem is now just a special case of Stokes' theorem. In fact, some people have advocated not even teaching Green's theorem anymore because Stokes' theorem covers it. Okay. Now, I do need to make a comment about orientation. So the curve C and the surface S must have consistent orientation, and which is similar to the positive orientation that we've seen in 2 dimensions. So, so what I mean by consistent orientation is if you are traversing the boundary of your curve, you can think of the little guy walking along the boundary curve, in such a way that he can see the normal vector. So in this case, he's walking on top of a boundary, and the normal vector is also pointing upward in this case. So the orientation is consistent if the interior of a region in such a way that the normal vector can be seen. Is on the left. Okay. And the textbook actually describes a consistent but different, pardon the pun, literally rule of thumb. Kind of like the right-hand rule for getting a direction of a cross product. So, does anyone know what I'm even referring to? I guess if you've ever taken a physics class, you would. Okay. In fact, during the one physics class I took as an undergrad, I was in the middle of a test and I was trying to use a right-hand rule, but I was using my left hand because I was writing with my right. Yeah, and so I sympathize with students who think crazy things during tests. Okay, so what's going to happen is when you have a given curve C and surface S, you're going to go ahead and compute the normal vector in a way that we have of previous surface integrals. You have your parametric equations, x, y, and z, that are functions of u and v. You compute ru and rv, the partial derivatives, and then take their cross product to get the formula for n. And you'll see which way is it pointing. And then from your parametric equations of a curve C, you'll see which way you're traversing around the curve. So are those orientations consistent with one another in this manner? If they're not, then in order to properly apply Stokes Theorem, you have to change the sign of one of these integrals. Now, I will go through a number of examples, and you'll see how we make sure that we have the proper orientation. This is that orientation is a little harder to describe in 3D instead of 2D. 2D, you just have clockwise and counterclockwise. But once you get to 3 dimensions, it starts to lose its meaning. Okay. Now, to refresh your memory, and of course this will be on the formula sheet for the test, if you have a given vector field with components p, q, and r, then the curl of f turns out to be ry minus qz, pz minus rx, qx minus py. Okay. And what can be helpful about Stokes' theorem is whatever vector field you're given over the curve, you have to take partial derivatives of it to integrate over the interior surface. And sometimes that curl might give you a simpler integrand to deal with than what you had going around the curve. And maybe some things will go to 0. So for the first example, let f be vector field yz, xz, xy. And the surface S is the part of a paraboloid z is equal to 9 minus the quantity x squared plus y squared that lies above a plane z is equal to 5. Also, we have upward orientation. And remember how we handle upward versus downward orientation, that once we compute the normal vector, we have, that mean that the z components of your normal vector n cannot be negative, otherwise it's pointing down. Okay. Now, so if I were to draw this surface, by intersecting this paraboloid with a plane z equals 5, that defines a natural boundary. So we have x, y, z. So here's our paraboloid. It starts up at z equals 9, and the paraboloid faces opening downward from there. But up at z equals 5, we have our plane. So this intersection here marks the, okay, so here's your surface S, and that boundary there is C. Now, the normal is supposed to be pointing up. So the normal vector is perpendicular to the surface at each point. So this is your normal vector n with the correct orientation. So in order to use Stokes Theorem, the curve C is to be oriented in such a way that it's going to be, in this case, if you're looking down on the xy plane, it's going to be the usual counterclockwise orientation. So you have your guy walking along the boundary in such a way that he can see the normal vector. The interior of the region should be on his left. So for a situation like that with upward orientation, then it should be counterclockwise. On the other hand, if it's specified downward orientation, normal vectors will be pointing inward rather than outward, then the curve C should be going oriented the other way, clockwise. Okay. Now, if we look at, so what we have by Stokes Theorem, we have the integral of the curl of f over the surface must be equal to the line integral over this curve C of f dr. Okay. Now, if you look at try to get an understanding of this curve C, that is the intersection of z equals 9 minus x squared plus y squared, and z is equal to 5. So to understand the x and y to satisfy this, you should set these equal to each other. So we have 9 minus x squared plus y squared is equal to 5. So what is this curve? If we simplify this. Yeah, it's just a circle of radius what? What? Yes, radius 2. Because you get x squared plus y squared is equal to 4, so you have a circle of radius 2. So as far as parametric equations, we have x, as usual orientation. X is equal to 2 cosine t, y is equal to 2 sine t, and t goes from 0 to 2 pi. We go all the way around. What's z? This is a curve in three-dimensional space. We have to have parametric equations for x, y, and z. So what would it be here? The answer's on the board. Yeah. It's here, contained in this plane, z equals 5. Okay. So then this would lead to your tangent vector. So dx, you just take the derivatives of all these with respect to t. So you'd have minus 2 sine t dt. dy is 2 cosine t dt. And then dz is 0. Because the way you would express this line integral would be the integral from 0 to 2 pi, and you'd have, okay, your vector field f is over there, so you'd have yz dx plus xz dy plus xy dz, but then you have to express all of this in terms of t. So y would be 2 sine t, z would be 5, and then dx would be minus 2 sine t dt. That's the first term. And then you would fill in the other terms in a similar way. You have 2 cosine t times 5 times 2 sine t. No. Wait. Y sine dx. Okay, sorry. dy is 2 cosine t. And then the rest of this term, this would be 0 because dz is equal to 0. So this is all that you would have. And then you can go ahead and evaluate the integral from there. An interesting trig identity comes out because after you simplify this as much as you can, you have 2 times 5 times 2 is 20 in both terms that you can pull out. And you get sine squared, or actually you get minus sine squared plus cosine squared. How does that simplify?
-1.
You wish. No. Cosine squared plus sine squared is 1. When they're the same sign, you get 1. But they're different signs now. I don't suppose anyone remembers that trig identity. So in general, cosine squared theta minus sine squared theta is equal to cosine 2 theta. So it's a double angle formula for cosine. There are 3 different double angle formulas. It's the easiest one to remember. So that minus makes life harder for you. But then, at least by writing it as cosine 2t, then the integral is easy to work out from there. However, well, first any questions about how, if you're doing this by a line integral, how that was set up? Now, for the surface, if you were to evaluate this way instead, you would need parametric equations for this surface. At least, so what you could do is, this whole surface is contained within a cylinder. So x squared plus y squared are limited from 0 to 4. So for the surface S, what you could do is say x is equal to u cosine v, y is equal to u sine v, where u goes from 0 to 2, v goes from 0 to 2 pi. So you're parametrizing the disk in polar coordinates, the disk of radius 2. But what about z? For z, you go to the equation for the paraboloid, and you get 9 minus x squared plus y squared, which is just u squared. So those are parametric equations of the surface, and normally what you would do is compute the normal vector. Now, just for practice sake, I'm going to go ahead and do it, and then I'll be able to show you why that was a stupid idea. So to get to normal vector, which is normally what you need for surface integrals, as we've seen, you compute RU, which is cosine V, sine V, and then minus 2u. And then RV would be minus u sine V, u cosine V, and 0. And then you would take the cross product of these to get the normal vector. And at least there's a 0 here, that helps. So your normal vector, RU cross RV, would hopefully simplify using cosine squared plus sine squared equals 1. So we have minus 2u squared cosine V. Second component is 2u squared sine V. And then we have u cosine squared plus u sine squared. So that simplifies to u. And the only reason I did this is to see the z component. Do we get something that's positive or negative? It's positive. So this is a normal vector we want. It is upward orientation because u is between 0 and 2. So in fact, when u is, when we're, okay. Okay, so when u is equal to 2, this is interesting. Okay. Yep, that takes care of a disk. Z is 9 minus u squared. Okay. This particular normal vector is not looking quite like I expected it to. Because, for instance, suppose that x and y are equal to 0, then that would only happen if u is 0 and then z is equal to 9. So you're up at this point right here. But then the normal vector you'd think would be pointing straight up. But you actually get a normal vector that's all zeros. Okay. Now, as for why none of this is necessary, what we'd normally do to evaluate the surface integral, we would figure out the normal vector, which we did, and then figure out the curl of f, and then integrate that over the parameter space. U goes from 0 to 2, v goes from 0 to 2 pi. And, oh, I'm just about out of time. So I'll make this last point, and then I'll do more examples of this on Friday. That's all we have time for, all we'll do. If you computed the curl of this, if you take this, and you figure out these partial derivatives, what would you get? Like, this is your P, Q, and R. So for instance, what is Ry minus QZ? It's 0. And in fact, if you reduce the other components, you get 0. So in fact, this is a conservative vector field. F is the gradient of xyz, which you would see if you integrate this with respect to x, respect to y, respect to z. Therefore, the curl of any gradient is 0. Therefore, both of these integrals are 0. But this is good practice working in parametric equations anyway. I'll have more interesting examples for you on Friday.